So good evening, everybody. I'm Frank Petrie, president of Battle Point Astronomical Association, and thank you all for joining us tonight. We're going to hear from Michaela.
All right, sounds good. Thanks, Frank. All right. So, good evening, everyone. And I'd like to thank Frank and the BPAA folks for having me today. My name is Michaela Leung. I'm from Bainbridge Island, and I was an active BPAA member about 7 or 8 years ago. So some of you may know me, and to some of you, I may be a new face. But today, I am a PhD student at the University of California, Riverside, where I study planetary astrobiology, and specifically, I work on increasing the tools that we can use to determine if there is life on planets around other stars. Before beginning my talk here, I would just like to take a moment to acknowledge that I'm speaking to you today from the unceded ancestral homelands of the Gabrielino, Tongva, and Kivitz peoples, who are the past, present, and future caretakers of this land. So moving on to a quick overview. So first I'll be talking a little bit about me, a little bit about my path to where I am today. And for some of you, this will be since you last saw me, and for some of you, it will just be a story about how I've gotten to where I am today. I'll also be talking about finding exoplanets, characterizing exoplanets, and then habitability and biosignatures, which is specifically the part of this talk that's interested in talking about life beyond our solar system. So when I was most involved at BPAA was when I was in middle school. I was borrowing telescopes from BPAA, and I seem to remember that I spent a little bit of time learning how to use the Ritchie, but all I really remember was to not crash it into the dome. But you know, it's not the worst thing to take away from that. From there, I actually went on to Bainbridge High School. And while I was there, I also had the opportunity to work at the Pacific Science Center, where I was able to share my love of science and specifically astronomy with many people. Rather than finishing high school, I actually went on to UW's early entrance program. And while at UW, and while I was working at the Pacific Science Center, I had the opportunity to visit the Monash Ridge Observatory a couple of times. An MRO is UW's training telescope for observational astronomers, and that's what's being shown in this center picture here. I also got involved while I was in undergrad with exoplanet research, and this is me standing next to a poster of mine that I worked on while I was an undergrad. And finally, I consider myself to be a planetary scientist rather than strictly an astronomer. And so I also work on planetary processes, and that includes thinking about the past of our own Earth. And so the picture on the right actually shows me at a remote site in Montana, where I was collecting dinosaur and early mammal bones. And specifically in this image, right where my finger is, I'm pointing at the ash layer in the rock record that marks the KPG mass extinction, which is most famous for having killed the dinosaurs. So I actually had the opportunity to do a lot of really interesting things while I was in undergrad, including working on some projects that basically set me on the astrobiology path that I'm on now. So almost exactly a year ago today, I graduated from UW with a Bachelor's of Science in Earth and Space Sciences with a concentration in biology. That again is sort of that connection really to looking for life beyond the Earth. Since then, I moved to California to do school from my desk. The picture on the left shows me at my first day of grad school in my house. I still haven't seen my office or anything, but well, we're getting there. And the right side shows actually just a little telescope that we got last fall. And hopefully we'll be able to take that out soon and get some observing in before the fire season here gets too bad. That's enough about me. So moving on to talking about exoplanets. So most simply, exoplanets are planets around stars other than our sun. And exoplanets are the main place that we look for life outside of our solar system. And this is primarily because we believe it's the planetary environment that really offers a safe place for life to originate and evolve. So there are a number of methods that we use to find exoplanets. One thing I wanted to emphasize here is that even with current telescopes, we cannot directly image exoplanets. You can't, unfortunately, just take your telescope outside and point it at an exoplanet and look at what's going on there. So the methods that we use to find exoplanets are primarily indirect methods. And so the two main methods I'll be talking about are the transit method and the radial velocity method. And so beginning with the transit method, this slide shows essentially a diagram of the transit of a planetary transit. And a transit is what occurs when a planet passes between its host star and the observer. And this drop in light is what is recorded as a result of that. And if that drop in light occurs regularly over about the same period of time, you can kind of extract that signal from this star observation, and you can determine, one, that there is a planet there, and then also the planetary radius and orbital distance, which are really useful for thinking about the size of the planet and what some of its conditions might be. Another one of the main methods that's used to find exoplanets is what's called the radial velocity method. And radial velocity specifically refers to the part of the part of the star's orbit that is pointed directly at the observer. And this is once again an indirect impact from a planet that we can't observe, but essentially the mass of a planet will pull on its host star in such a way that the light waves that are observed are either shifted towards the red or to the blue, depending on where the planet is in its orbit relative to the observer. And this is again something where periodically you would be able to see those red shifts and blue shifts, and again extract information about the location of the planet and its mass, specifically because it's the mass that's responsible for pulling on the star. These are also sometimes called the wink and wobble methods in terms of how they sort of impact stars. So this is a quick diagram courtesy of the Exoplanet Archive, which is housed at Caltech. And as you can see here, there are nearly 4,500 current confirmed exoplanets. And by confirmed exoplanets, that actually means that there have been follow-up observations after an exoplanet candidate was identified, and those follow-up observations have also found the exoplanet. So that eliminates, the results of error or anomalous readings from telescopes. One thing you might notice along the x-axis here is that exoplanet science is a very young field. So the first exoplanet was found in 1989. But the founding of exoplanet astrobiology as a serious field didn't really take off until 1995, when the first exoplanet around a sun-like star was discovered. And that planet was called 51 Pegasus b, and it's kind of a very famous name in the astrobiological community because it was that first planet around a sun-like star. And you'll notice that these numbers have really taken off in about the past 10 years. We've seen these really big spikes in the number of known exoplanets. And so this really shows that the exoplanet science field is growing very rapidly right now. So this is a graphic from a few years ago when there were fewer exoplanets. Unfortunately, the exoplanet field grows so quickly that the graphics are not always kept up to date. So don't worry too much about these numbers. But what essentially we're looking at here are the main size categories of exoplanets. So these are split into Mercury or Mercurian planets, these sub-Terran or smaller than Earth planets, the Terran-sized planets, and then the super-Terran, Neptunian, and Jovian planets. And you'll see the main two categories of gas giants and terrestrial planets are sort of picked out there at the top. And this is a rough sense of the actual size to scale of these planets. And you'll notice that there are significantly more planets detected in that larger size. Part of that, though, is due to observational bias. So these larger planets have a much larger impact on their host stars. And because we're observing the host stars, the larger planets produce signals that are easier to detect. But at this point, we have significant enough numbers of exoplanets that we can sort of start to look at their demographics, where the groups break down and what kind of patterns we see. So these are showing the same groups as we were looking at before, and they're actually also now being separated by their surface temperature. So we have the hot zone, which is where Venus and Mercury orbit today. We have the warm or habitable zone where Earth and Mars are located, which I'll talk more about later. And then we have the cold zone, which in our solar system is where we see the gas giant planets. And what's really interesting is there are a number of types of exoplanets we see here that are not represented in our solar system. And the largest example of this may be the super Earth class of planets. And this super Earth class of planets is sort of right at the boundary between being gas giants and terrestrial planets. And that is because it's right at the area where these planets can accumulate enough mass to hold hydrogen and helium atmospheres like a gas giant, but they may also still be small enough to be primarily rocky like the terrestrial planets. And the super Earths are not represented at nothing even close to a super Earth is seen in our solar system. So that's been a really surprising discovery about the existence of these super Earth planets. Another group is these hot gas giant planets. So like I said just a moment ago, in our solar system, the gas giants are found primarily in a cold region. But in these other exoplanet systems, we do see a lot of hot gas giants. And again, these hot gas giants are probably a little bit overrepresented simply because they're easier to detect. But it's still very interesting that we have these multiple groups of planets that we don't see represented in our own solar system. And we use our own solar system as kind of the model for understanding planetary systems. But these unique types of planets we're seeing elsewhere sort of maybe call that into question a little bit and maybe generate more scenarios for planet formation and the evolution of a stellar disk. So those are some really interesting takeaways from the demographics of these exoplanets. And one other thing to notice is the stellar systems right up here. So you'll note that there are a number of multi-planet systems, but the single planet systems do seem to dominate the number where we have observed exoplanets. That again may be an observational artifact because we haven't yet looked at all of these planets potentially for long enough to see a smaller planet or a further away planet. But it is interesting to see that there are few solar systems, again, that look like our own. And so just jumping back to this graph, so if you'll see here, there's right around 2012, 2013, there's a first big jump in the number of exoplanets and the number of known exoplanets. And then, there's also been this big jump about like 5 years ago, around 2016, 2017. And those jumps are actually just a product of the techniques that we use to look for exoplanets. And so at the top here, this is the Transiting Exoplanet Survey Satellite, or TESS, and at the bottom here is the Kepler Space Telescope. And Kepler was launched in, I believe, around 2012, and it was decommissioned not that long ago when it unfortunately had a number of mechanical failings and was no longer able to be used. But TESS is actually currently active and only began reporting its data in the past couple of years. And these satellites are really unique because the observations from Kepler really changed our understanding of exoplanets. Kepler pointed primarily at one section of the sky, and what we learned from that is that most star systems do actually have planets, which is really surprising considering, like 30 years ago, we didn't really know if there were any exoplanets at all. And in fact, TESS is going to survey the entire sky. And so it's been divided into a number of sections, and essentially TESS is methodically moving through, doing long period observations to look for those dips in light that show planetary transits. And then ground-based observers typically do the follow-ups from TESS. And in fact, some of my collaborators here at UCR work on following up from TESS with the Keck Space Telescope in Hawaii. One thing I wanted to also bring up for those of you all who are observers is this map of the location of stars with potentially habitable exoplanets. And we have, it's a declination and right ascension map. And you'll note that the distribution of the planets doesn't seem to follow any particular trend except for this Kepler cluster over here. But that cluster doesn't represent an actual group. It just represents the area of the sky that Kepler looked at. And so these are some potentially habitable exoplanets that unfortunately we can't yet detect, but you could if you wanted to well, not tonight since I hear it's cloudy, but otherwise you could go and look at these stars and maybe even do some citizen science if you were interested. So moving on from finding exoplanets to thinking about characterizing exoplanets. So characterizing exoplanets really refers to our efforts to understand what is going on both in an exoplanet's atmosphere as well as on its surface, and especially if those processes relate to life. And the main tool that we use to do that are spectra, and spectra are just measurements of the wavelengths of light that are absorbed or emitted from a planet's atmosphere. And what you're seeing right here is an Earth spectrum. And this is actually an Earth shine spectrum, which is obtained in a really cool way. It's actually from observing the light from the Earth that is reflected off of the moon to simulate Earth as an exoplanet from the ground. There are other ways to simulate Earth as an exoplanet, and those primarily use satellites or observations from outer solar system missions, sort of looking back at the Earth. But this Earth spectrum was actually generated from the ground, which is pretty cool. And you'll see there are a number, this is on the y-axis, you're seeing the brightness or measurement essentially of how much light your telescope or your spectrometer, as the instruments for this are called, is receiving. And then on the x-axis, you see the wavelength of light stretching here from the optical into the near infrared. And these features represent changes in the amount of light that can be detected by your telescope, and those changes are due to atmospheric absorption by various compounds. And this diagram is nicely labeled, showing carbon dioxide, methane, oxygen and ozone, water vapor, these various processes that impact our atmosphere. And the impacts of those atmospheres actually just have to do essentially with fundamental physics. And so those are things that we can both model and study to really understand what these features in atmospheres mean, and how we can best interpret them. So like I mentioned earlier, it's not currently possible to directly image these exoplanets. Direct imaging is only possible for potentially a few of the largest exoplanets, but those are things like the gas giants that I don't personally find as interesting. So I'll be talking primarily about terrestrial exoplanets for the rest of today's talk. And terrestrial exoplanets, we're really reliant on something called transmission spectroscopy. So returning to the transits we talked about a few minutes ago, like I said, we can use those to detect planets, but we can also use them to indirectly observe their atmospheres. And the way that's done is from observing transits, observing when the planet is eclipsed by the star, and then subtracting those out essentially to extract the spectrum of the planet. And that's what's actually being shown in this small figure down here. These black lines represent the data, and these blue lines essentially show a model that is being fit to those data. And those models are called forward models, and this process is known as an atmospheric retrieval. And what it's doing is essentially running a model across a large parameter space of different atmospheric compositions and processes to find what best matches. And that is how we can understand what's going on in planetary atmospheres. For example, at 1.27 microns, which is right about here, there's an oxygen absorption feature. And I believe that is what is being shown right here. And so you could look at the spectrum and say, okay, yeah, the atmosphere that best fits it has oxygen. And so we can say that this planet likely has oxygen in its atmosphere. Now, unfortunately, terrestrial exoplanets are very, very small. And because they're small, they don't produce large signals. Even when they're moving across the star, they're changing the star by a couple of hundred parts per million. And unfortunately, even with the best telescopes we have today, that's not really enough to get these spectra that we can use to understand the planets. However, in the coming years to decades, that should significantly change. So NASA's current flagship space-based telescope is the Hubble Space Telescope, which has been there since the 1990s. And later this year, hopefully, will be the launch of the James Webb Space Telescope, which will essentially replace Hubble as NASA's leading space-based telescope And James Webb will be a huge step up from Hubble, but even James Webb will only be able to potentially detect a couple of atmospheric features on a couple of exoplanets. So unfortunately, James Webb will not, it will enable us to look at a handful of exoplanets, but it won't really enable the kind of understanding at a large scale of what's really out there. Another thing to consider about the James Webb Space Telescope is that it was originally supposed to launch in 2010, and it is still not up there. So James Webb has been delayed for such a long time that the technology that we have now is actually better than what will be going to space, but unfortunately, it's been locked in with the sort of capabilities that it has now. Another significant increase to the observational capabilities will be the extremely large telescope class of telescopes. And this is going to be a ground-based class of 30-meter telescopes, and they can be used for high-resolution observations from the ground. Unfortunately, on the ground, you have to contend with things like the atmosphere, but these high-resolution observations can potentially shed light where James Webb cannot, simply because the much larger mirror is able to just absorb more photons and essentially get signals that might not be as possible with James Webb. But really, to get to the point where we can actually survey large numbers of exoplanets and really begin to characterize their atmospheres at a significant level to really understand what's going on there and to specifically answer questions about life, we are unfortunately reliant on NASA choosing a next generation space telescope that is suitable for looking at exoplanets. So what you'll see here is the primary mirror of the Hubble Space Telescope, which is 2.4 meters. The primary mirror of James Webb, which is 6.5 meters in diameter. And then this big mirror is the primary mirror for the proposed Large Ultraviolet Optical Infrared Surveyor, or LUVOIR, and this is 15 meters across. And LUVOIR would launch in 2035 or later. And actually right now, NASA is doing review panel decisions of what the next generation space telescope will be. And so exoplanet scientists are optimistic that they will choose either LUVOIR or HABEX, which I believe is the Habitable Exoplanet Imager or something like that. But there are other telescopes in contention, and if one of those are selected, we're going to be waiting even longer to look at this telescope data. So you might be wondering, okay, so you don't have any data, so what exactly is it that you do? And the answer is, I work on models. And models right now are the primary way we have to understand and establish frameworks for understanding planets beyond the Earth, and specifically thinking about life and how we can analyze it and look for its presence. So the models highlighted in orange are the models that I work with and will be describing the most. So we'll start with the one-dimensional climate and photochemical models. So these are simplified models that use physical and chemical equations to look at the atmospheric composition and structure, and particularly how it evolves over time, as well as looking at things like the temperature, the pressure, and the altitude. These are essentially build your own planetary atmosphere. You put in various parameters, and the model kind of develops consistent atmospheres based on how we know, chemical reactions go and things like that. The other main set of models I work on are what's called radiative transfer models, and they simulate atmospheric absorbance, and they generate modeled spectra. And so these are essentially simulated observations of the observations we hope to make with next generation space telescopes. And I'll be talking a little bit more about these spectra later, but they're also used to inform instrumental design and to kind of, again, get a better sense for what we would, if certain telescopes are selected, what we would be able to observe with them and how we would then be able to potentially interpret that. There are a number of other kinds of exoplanet models, one of which was 3D GCMs, or global circulation models. And these are adapted from really complex models that are used for the Earth. That's how a lot of processes like climate change, ocean currents, weather, things like that are studied, is primarily using the GCMs. And the 3D GCMs will provide a lot of fine detail about the planet, but they take a long time to run. and are a little bit more difficult for extreme cases just because they're optimized to work for the Earth. And so I primarily work on the one-dimensional models where you lose a lot of that like resolution. You essentially assume conditions are averaged across the planet, but you can explore a lot more parameters and run things a lot faster, even if they are sort of more just approximations. We also use instrumental models to further constrain our potential observations. So any instrument, as I'm sure many of you are aware, will introduce potentially noise, error, or will just have limitations in like what it is able to view. And so the instrumental models are really key for understanding how long, how many transits with James Webb would it take to observe this atmosphere, or what would be the signal to noise ratio there. And if the signal to noise ratio is too high, you're really not able to extract any meaningful data from your observation. We'll also use orbital models to look at the interaction between the planet and the star, and if it has other planets in its neighborhood, essentially what's going on with those. One thing that is particularly interesting is the idea of tidal locking, and tidal locking is when the rotation period of the exoplanet is the same as its orbital period. And what that results in is one face being locked towards the star and one face being locked towards essentially the darkness. And this is the same case with our moon. That's why we only see one side of the moon. But for an exoplanet, it can be potentially much more extreme because one side is essentially being baked while the other side is frozen. And there are ways with atmospheres and oceans that you can sort of get past those extreme conditions, but it's still really important to understand what kinds of conditions these planets could be undergoing before we're actually able to look at any data from them. And another category is interior atmosphere models. And what interior atmosphere models look at is primarily the impact of volcanoes and plate tectonics on releasing gases or changing surface processes in a way that influences the atmosphere. And that's primarily to understand long-term evolution of planets, because we know a lot about the evolution of the Earth, but not all planets, as we've seen, are Earth-like or will follow Earth-like evolutions. And so these models are meant to also help us understand, even if a planet looks potentially habitable now, in its past, it may have been completely different. And that has implications essentially for life, because life takes a long time to both originate and evolve. So moving on then to talking specifically about biosignatures and habitability. So we talked earlier about looking for planets, and I want to bring that question back up and instead propose the question, where do we look for habitable planets? And the answer for primarily astronomers and planetary scientists is that we look for Earth-like planets around sun-like stars. And one way that that is done is with what's called the traditional habitable zone that focuses on the presence of surface liquid water. And this is because we believe that a key dependency for life as we know it is the existence of surface liquid water. And so the habitable zone is the distance from a star where the surface liquid water can exist. And it's sometimes also called the Goldilocks zone because it has to be not too close to the star where the water will evaporate, but not too far away or the planet will freeze over. And so it's this really specific range of distances from a star, and it varies really significantly with the type of star. And so we're just going to touch briefly on star types here. And so in general, this is a Hertzog-Russell diagram, and it shows luminosity on the y-axis and surface temperature along the x-axis. And the main sequence where most stars live out their lifetimes is shown here, sort of diagonally through the middle. And when we talk about looking for sun-like stars, we're primarily talking about FGKM stars. And these are the cooler and redder kind of end half of the main sequence here. And we look for those stars partially because we believe they are sun-like, and partially because, like I said before, larger planets are easier to detect because they impact their stars more. And so similarly, it's easier to look at planets around smaller stars because any planet will have a more significant impact. And so I primarily work on FGKM stars because of that connection with Earth-like planets and Sun-like stars. So looking at our own solar system, this right here shows a diagram of the habitable zone in our own solar system. And you'll notice that the Earth and Mars are included in the habitable zone. And that's partially why there's so much interest in sending, like 30 missions to Mars to look for life there, is because it really is the only other place in our solar system that exists in the traditional liquid water habitable zone. One thing that is, however, interesting to note is that earlier in the sun's history, it was dimmer. Stars get brighter and hotter as they age. And so Venus was actually in the habitable zone earlier in its history. And in fact, the leading theory among planetary scientists right now is that Venus was actually habitable for 1 to 3 billion years. And so there are 3 new missions to Venus that were announced within the past 2 weeks or so. And they're pretty much all going there to find out what went wrong on Venus. Venus is sometimes called, the exoplanet in our backyard because it's so close to us and so similar to us in so many ways. But the evolutionary trajectory of Venus turned out very differently. There's a famous quote that goes like, if Venus was not in our solar system, we wouldn't dare imagine it, because the conditions seen on Venus are so extreme and so different from what we see here on the Earth that, were it not for Venus, we might think even more broadly about conditions that might be habitable. And so Venus is a really good cautionary lesson, even though it's not in the habitable zone today. And so thinking about the habitable zone boundaries for different star types, because like I said, the habitable zone boundaries depend really significantly on the star types. And so you'll see 4 lines here, and those represent the conservative and optimistic boundaries for the habitable zone. So from runaway greenhouse to maximum greenhouse is what's considered the conservative habitable zone. And then from early Mars to recent Venus is what's considered the optimistic habitable zone. And those boundaries are essentially set by what assumptions you're willing to make about planetary formation and evolution, and basically what extreme conditions that planets can tolerate. And you'll notice that these lines sort of bend inward for these cooler stars. And that's just because red stars like M and K dwarfs will peak in the infrared, which is what drives the climate. And so there's less light needed overall, just because more of it's peaking in the infrared wavelengths. And you'll notice that the Earth, Mars, and Venus are up here. The temperature of the sun is almost 6,000 degrees Kelvin, but most of the exoplanets on this diagram are actually down here below 4,000 degrees Kelvin. And this is in the range of M dwarf stars primarily, and that's again because they're the smallest kind of star that is most impacted by having a planet. And you'll notice way down here at the bottom is the TRAPPIST-1 system. And the TRAPPIST-1 system is actually very exciting, partially for one reason, it has 7 exoplanets. And so it's probably one of the closest systems we've found to being like ours. And as you saw on the last slide down here, as many as 4 of those planets could be habitable. And so it's really useful for astronomers to be able to observe that many planets in one system, and then to also be able to compare the evolution of those planets. And in fact, TRAPPIST-1 is very cool and very small. It pretty much barely reaches the minimum threshold for hydrogen burning, which is necessary, of course, for the luminosity of a star. And in fact, when the James Webb Space Telescope launches later this year, one of the first things it will observe is the TRAPPIST-1 system, because there is so much interest from exoplanet scientists in learning more about the TRAPPIST-1 system. And so hopefully we'll actually have a lot of questions about TRAPPIST-1 and about what's called comparative planetology, which is essentially comparing planets' evolutionary paths. And hopefully we'll have more information about all of those in the next year or so. One thing I really wanted to stress before we move on here is that just because a planet is habitable does not mean that there is life there, which of course, a prime example of this is Mars, right? Mars is in our habitable zone today, but we don't currently believe there is life there now. And really, all the habitable zone in the context that I've used it today really refers to is the presence of surface liquid water. And that ultimately only means surface liquid water. And so, better constraining what habitability means and how we should actually rank and identify the best targets for these next generation space missions when we do have access to them is actually one of the key topics in current astrobiology discussions. And it actually kind of leads a lot of the goals moving forward in the community to sort of better set expectations and kind of parameters for what should be considered habitable and what we should look at first. Another sort of problem that potentially comes up is that the conditions that are necessary to support life are not the same conditions where life can start. And so on the left-hand side, you see an artist's impression of the Archean Earth from about 3.5 billion years ago. On the right, this is just an image of the modern Earth. And we believe that life started 3.5 billion years ago on the Earth in the Archean, but the conditions on that planet were very different than they are today. And so that adds kind of an extra step towards thinking about habitable planets, is also thinking about their pasts and if they actually may have had the right conditions for life to arise, because we sort of need both of these conditions in this order to exist to get life, at least life as we know it here on the Earth. So moving on from the idea of where we look for habitable planets, let's talk about how we would actually detect signs of life. And the main way that that's done is through atmospheric biosignatures, which are actually defined as detectable signs of life in exoplanet atmospheres. And these are typically just atmospheric absorption features of gases that are known to be connected to life. And so bringing back this diagram of the Earth that we showed earlier, you'll see, for example, oxygen and ozone are considered to be a strong biosignature candidate, as well as methane, because that's connected to anaerobic bacteria. But there are also other things like what's labeled here as the vegetation jump or the vegetation red edge, which actually shows the impact of land plants on the Earth's surface. And that impact is actually so significant that it does change the way the light that we reflect off of the planet. Unfortunately, though, biosignatures are much more complicated than that. We can look at the Earth's spectrum, right, and say, oh, there's oxygen there, and we know that oxygen is there from life, so oxygen is the biosignature. And unfortunately, it's not quite that straightforward. So I'm going to walk us through an example looking at some of the issues you can run into with biosignatures. And so we're starting off here with cyanobacteria, which are one of the simplest forms of life here on the Earth. We think cyanobacteria have probably been around for a very long time. And cyanobacteria perform what's called oxygenic photosynthesis, which I'm sure many of you are familiar with, one of the byproducts of which is oxygen. And that oxygen has actually been so significant in the past, 3.5 billion years on the Earth that our atmosphere is 21% oxygen. But unfortunately, there are a number of false positives. So scenarios that we can get that where there is no life, but the observation looks very similar to one where there is life. And so this really gets into the idea of false positives, which you may be familiar with from statistics or even from various discussions of things like COVID tests, because those are something that can come into play there as well. And so looking at this diagram, right on the horizontal axis is the ground truth. And so, that's, if we went to this exoplanet, we would either find life or we wouldn't find life. And that's the ultimate ground truth of what's actually happening there. On the vertical axis is what's being detected. And, are we detecting and interpreting something that we think is life or something that we don't think is life? And you'll see here we have false positive, true positive, false negative, and true negative. And those are the 4 cases that you can kind of get when using this sort of detected versus ground truth framework. Unfortunately, in the foreseeable future, we will not be able to go to exoplanets. And so without knowing what the ground truth is on the exoplanets, we're then completely reliant on our detections and interpretations to differentiate between the presence of life and its absence. And so we really need to have an understanding of what kind of false positive scenarios can exist and how we can differentiate those from a photosynthetic biosphere, specifically in the case of oxygen, like we see here on the Earth. And this is essentially a representation of what that would mean. It's eliminating through other observations or models or calculations, eliminating these false positive and false negative scenarios until what we detect is equivalent to the ground truth. And so what that really, one of the main ways we do that is through reducing false positive potential. And so moving back to our oxygen example, there are actually a number of false positives for high oxygen atmospheres. So like I said a few minutes ago, we have a high oxygen atmosphere here because we have life, and that life is producing oxygen into the atmosphere. But there are other ways to get oxygen in the atmosphere, one of which is a process called ocean loss. So specifically around M-dwarf stars, early in their lifetimes, they burn very hot and very bright. And what that can lead to is a runaway greenhouse effect on the exoplanet. And in a runaway greenhouse, the exoplanet keeps getting hotter and hotter, and the feedbacks on it just continue to push it more in the greenhouse direction. And so what that will actually result in is the ocean boiling off of the planet. And in fact, this can be as many as 10 Earth oceans worth of water. And this is the idea of ocean loss as first coined by Luger and Barnes in 2015. And once this ocean boils off, it goes into the atmosphere, and in the atmosphere, it can interact with UV radiation. UV radiation is very high energy, and so it's dangerous, right? The UV radiation can split bonds, and that's why it can be dangerous to humans, because it can split up things in your body that aren't supposed to be split up. But specifically in the case of water, it will just split into hydrogen and oxygen. Hydrogen is very light, and so it will essentially just escape to space and kind of just float off into nothing. And so over time, all of that hydrogen will be lost, and you will have these high levels of oxygen build up in the atmosphere. And so now you have a high oxygen planet, but there's life nowhere in sight. And so one of the ways that we think about addressing this problem is through modeling these planets and comparing what those observations would look like. And so what you see here on this slide is modeled spectra of two oxygen gas absorption features. On the x-axis, you're seeing the wavelengths where this light is being measured. And on the y-axis, you're seeing reflectance, which is a measurement of how much light is being reflected by this planet. So these are simulations of Proxima Centauri b, which is the closest exoplanet to us. And these simulations are done for reflected light. So it's for direct imaging, which is not currently possible. And these blue lines show the Earth-like or inhabited planet case, and the orange lines show the post-ocean loss case. And you can see in the right-hand figure that both cases have roughly similar depths and approximately the same feature shapes overall. And these are, in fact, very high-resolution spectra, similar to what you would get with an extremely large telescope. But if you were observing with a smaller telescope, you may very well get features that look exactly the same for both cases. And that is a problem, right? Because if you detect that feature, then it's not clear if what you're seeing is post-ocean loss, if what you're seeing is oxygen produced by life. However, at this band, which is at 1.27 microns, you actually have very strong reflectance from the Earth-like biosphere, but you have almost no reflectance in a post-ocean loss planet. And that actually is because in that post-ocean loss planet, the levels of oxygen are so high that collisions between the oxygen molecules are inducing additional absorption. And so nearly all of the light is absorbed at this wavelength because of the high levels of oxygen. And so what this kind of lays out is a process that through observing both of these areas, you could differentiate between an ocean loss planet and a photosynthetic biosphere. Primarily, it has to be both of them because, like I mentioned before, if you just observe the oxygen B band, you wouldn't be able to differentiate the cases. But if you just observed the 1.27 micron band, you might not, you could, the amount of reflected light from the post-ocean loss case is so low that it could also be confused for a planet where there is no oxygen. And so you need both of these observations to demonstrate that there is in fact oxygen in the atmosphere and that that oxygen is actually at such high levels that you're getting this oxygen collisionally induced absorption, as it's called. And in fact, this is the main result from a project that I worked on as an undergrad at the UW that was published in the Astronomical Journal by the American Astronomical Society about a year ago. And that was sort of my first foray into working on these kinds of projects and things. It's also my only project that's finished. So everything else is sort of still a little bit in flux. But some of those projects that I also wanted to mention include, number one, expanding the idea of the habitable zone for circumbinary planets. And so circumbinary planets are planets that orbit two stars. And of course, the most famous example of this is the planet Tatooine from Star Wars, where you have a twin sunrise or twin sunset. And there are actually a number of complications that arise from having two stars, especially if those stars are different types. So if they have significantly different masses, they peak at different wavelengths and will have pretty different impacts on those planets versus having a single star like we see in our own solar system. And so that's one of my main projects that I'm working on finishing up right now. Another project that I'm working on looks at novel biosignature candidates. So oxygen is not the only biosignature. We also will use things like ozone, nitrous oxide, methyl chloride, methane, but we need more essentially because there's no guarantee that we'll be able to observe oxygen or any of these other gases. And a lot of these other gases have problems like I just outlined with oxygen, where there are strong false positive potentials or other absorbing features which could easily be confused for a biosignature. And one example of this is the recent purported detections of phosphine in the atmosphere of Venus, which were somewhat widely hailed as a sign of life on Venus. But unfortunately, phosphine, which is what they again claim to have detected, absorbs at a very similar spot in the spectrum to sulfur dioxide. And sulfur dioxide makes up a very large percentage of Venus's atmosphere. And so it seems very likely, based on some models and reanalysis of those data, that what they actually detected was sulfur dioxide that they mistook for phosphine in their excitement to look for life on Venus. And so we really need more biosignatures that are more unambiguous to prevent those problems. And so that's what I'm working on. Additionally, is analyzing the feasibility and use cases for novel biosignature candidates. And then finally, one of the other projects that I'm working on is looking at atmospheric modeling of planets around specifically M dwarfs as part of a large project that my advisor is funded to do. And that's specifically focused on M dwarfs because they will be the first place that we can really thoroughly observe and where we would be able to potentially start looking for biosignatures. One topic that I wanted to also cover today is the idea of technosignatures. So what I've been talking about so far are biosignatures, which are signs of life. And this includes things like simple life, like cyanobacteria, plants, or even animals, whereas technosignatures look for signs of an intelligent civilization. And this can vary a lot. It can include things like looking for artificial products in the planet's atmosphere in a similar way that we do for biosignatures. And one leading candidate for that is chlorofluorocarbons, which we used to have a problem with in our own atmosphere. And that's because we don't really think they can be produced naturally in high quantities. And so detecting chlorofluorocarbons in the atmosphere would likely point towards an intelligent civilization producing chlorofluorocarbons and putting them into their atmosphere. or a not so intelligent civilization, depending on the impact that the CFCs are having. Another project is what's called active and passive SETI, which is the sending of and listening for radio messages. And that is also sort of an effort in looking for techno signatures and then specifically listening. It's called the Breakthrough Listen Project, and harnesses the power of a number of different observatories around the world to listen for those radio signals. And then it starts to get into things that can get a little bit more fringe, like looking for laser lights on nearby exoplanets, or arguing that objects that pass through the solar system were built by aliens, or like, unfortunately, the technosignatures field can start to really blur into sort of the more science fiction kinds of things, but there are definitely like legitimate interests and projects looking at technosignatures, even though there is a little bit more of a fringe, and specifically when you're thinking about technosignatures. Although honestly, working on anything to do with astrobiology, you get contacted by conspiracy theorists who are like, I know aliens are out there. They talk to me every night. And you need to read my paper because it will like change your work. So that is just a part of the field because there's so much popular interest in it. Let's see, why is it not? Okay, and then another major caveat that I really wanted to touch on here is that biosignatures, and to a degree technosignatures, assume that life, when we find it, will be similar to the Earth, and especially in terms of its biochemistry. So this plot here is showing a red dot that indicates the Earth with a number of different lines in different directions passing through that. And what that essentially demonstrates is a point that, you know, any science or math teacher could tell you, which is that a single point does not define a line, and that from a single data point, you cannot assume a trend or sort of like extrapolate beyond that. But unfortunately, you know, with the Earth and with the common biochemistry that's shared by all of the life currently available on our planet, we don't really understand what life is. And so planetary scientists and astronomers primarily take the example of the Earth and look for a second Earth, look for an Earth-like planet. But there are other astrobiologists who work on the fundamental physics and chemistry necessary for life, and specifically life as we don't know it. And this is where you get into the spelling of life with a Y like that, which was coined by Bartlett and Leung in 2020 to specifically describe life that is biochemically different than our own. And I just wanted to make sure to mention that here because that is sort of a big area of basically unknown. We don't know what life could be like. And so it's also another one of the major branches of astrobiology, along with thinking about, you know, the origin of life on the Earth, looking for life in the solar system, looking into, you know, various extreme conditions on the Earth, and then as well as sort of the exoplanet planetary astrobiology side of things, which is where the work that I do falls. And then finally, I'll just leave you with this quote from Buckminster Fuller, which is, sometimes I think we're alone, sometimes I think we're not. And in either case, the thought is staggering. And I think that this quote really captures a lot of what excites so many people, both scientists and the general public, about astrobiology, is that it really gets at the answers to a lot of fundamentally like really philosophical human questions about, you know, our place in the universe. Are we alone in the universe? Is there other life or other, you know, intelligent life out there? And those are really overwhelming questions to ask, to think about, and to work on. And so I think, you know, we're really lucky to live in a day and age where we can start to answer those questions scientifically and begin to kind of chip away at answering those questions which have stood, you know, pretty much as long as humans have looked up at the sky. And with that, I would like to thank my advisor, Dr. Eddie Schwederman, the co-authors on the paper I mentioned earlier, Doctors Jacob Lustig-Jaeger and Victoria Meadows. I'd also like to thank all of you for coming today and listening to my talk. If you're interested in getting in touch with me after today, my contact information is down here in the corner. And with that, I'll take any questions that you guys might have.
All right. Thank you, Michaela. That was great. Wow, what a lot of information. That's really cool. Folks, if you have questions and you want to type them in the chat or use the raise hand button. I'll look for your hand up on the participants list and call on you one at a time. Okay, I see Jay's got his hand up, but before we get to you, Jay, Steve has a question he put in the chat a little bit ago. And can you see that, Michaela, in
Yes,
the
I
in the
do.
chat
I
box?
did
Go
see
ahead.
Yeah,
that there was something.
you answered it indirectly after I put it in. So go ahead.
Yeah. I was going to say I saw that something had popped up in the chat, but I hadn't checked on it. So yeah, the increased stellar variability and radiation bursts of small stars, they particularly drive atmospheric photochemistry. And I work primarily actually with photochemical models, and that's actually the last project that I mentioned that's working specifically like on M dwarfs. Primarily, what I'll be doing is looking at the impact of photochemistry in those atmospheres as part of getting like a really comprehensive picture. So yeah, that is something that we do try to think about.
Okay. Let's see. Another quick question in the chat. Do you know the distance to the nearest exoplanet?
Approximately 4 light years.
Four
It's
light
Proxima
years.
Centauri b.
Right. And and then they say, or habitable exoplanet. Well, we don't know of any habitable exoplanets.
Right. Well, I think, so Proxima Centauri is in the habitable zone of its star, but we have no idea like what's going on there, right? Like Proxima Centauri does produce a lot of the increased stellar variability and radiation bursts that Steve was mentioning. And so it's very possible that even though these planets are in the habitable zone, they might be sterilized by those processes or otherwise like impacted in a way that makes them not habitable. So
Yeah.
more information is needed to answer that question, I will say.
Okay. Let's see. So Jay has his hand up in the participants list. Go ahead, Jay. Unmute
Yeah,
yourself and yeah.
quick, I think, hopefully simple question. You talked about super Earths. How big can a super Earth get?
Yeah, so super Earths are typically considered 1.5 to 2.5 times the radius of the Earth, which translates to about 5 to 10 times the mass of the Earth. And that's because once you get substantially larger than that, you have so much mass that you're able to hold on to that hydrogen and helium atmosphere that really pushes you into the gas giant.
Okay, thank you.
Okay. And Dave Cuomo has a question. Go ahead, Dave. Unmute yourself.
Yeah, thank you, Michaela. I hope you can hear me right now.
Yeah.
That was very awesome. Wonderful talk. When you were showing the images of telescopes to detect biosignatures in exoplanets, you had the Hubble and, of course, the James Webb and the possible successor to the James Webb. And all of those are in the visible and infrared wavelengths. Are there biosignatures that are detectable outside of visible and infrared that other wavelengths might be useful?
So primarily, at least when you're talking about, again, like life as we know it, the most of the biosignatures that we've developed so far do observe pretty much exclusively in the visible and the infrared. Once you get into, the UV, you have things like ozone, but ozone has its own problems with atmospheric buildup and false positives. So it really is primarily within the visible to infrared that we've developed most biosignatures.
Okay.
Thank you.
Thanks, Dave.
And let's see. Joe Hutchings. Unmute yourself, Joe, and go ahead.
Michaela, it's really nice to see you again. Great job. I have a whole bunch of questions, but I'll try to limit it. My first one will just be a follow-up to what we were just talking about. You had mentioned that the Webb will be looking at the TRAPPIST system for understandable reasons, but Proxima b is even closer. Will it take a look at Proxima b as well? Is that a priority for the Webb?
Not in the first observing cycle. So the way James Webb and most major telescopes work is that you submit proposals for telescope time, and out of the proposals that were selected for the first cycle, TRAPPIST was selected, Proxima was not. There were a number of other exoplanets selected, but it was primarily more for continuing to like sort of survey rather than doing the in-depth atmospheric characterization as is most interesting to like biosignature scientists.
Okay. Thanks, Joe. And Glenn has a question. Go ahead, Glenn, unmute yourself.
Thanks, Michelle. Excellent talk. Got a question for you about, say, sulfate reducers. Looking at, black spunkers, which were discovered when I was an undergrad, crying out loud. I guess how would you detect, say, a sulfate reducing atmosphere? Since I didn't see anything about that in any of your slides, are people looking at that, or like the nitrate reducers, the sulfate reducers, things like that as potential life forms on exoplanets?
Yeah, so those are great questions. So actually, one of the biosignatures that I didn't mention is dimethyl sulfur, and another some other gases in kind of the methylated sulfur family. And those are actually essentially used in the context of thinking about more anaerobic processes and things like that. So it's not just like oxygenic photosynthesis and its products that are thought about, but that's was sort of like the first, I guess, area that was looked at, and so now it's some of these sort of like secondary processes that hold less life here on the Earth, but we're now starting to analyze those for things like sulfur. I don't know about nitrogen. I know like nitrous oxide and NO2 are nitrogen dioxide are also considered to be like, if not biosignatures, like proxies to biosignatures, but they're also very interesting because the nitrous oxide gases interact with ozone, and so those can also regulate your ozone processes, which is another potential area of like a false positive production, because you can get high production of ozone from these other gases that aren't necessarily high levels of oxygen being produced from the ground. I don't know if that answers your question. Sorry, I went off on a little bit of a tangent there.
No, that's great. I just, I've dealt with reducing bacteria in groundwater for years, and it's something that, really in the last 20 years or so, people have started thinking in terms of that. So
yeah,
just wondered what was happening off Earth.
Yeah, I am working on some biosignatures additionally that are sort of in the area of more reducing type things. I'm just not allowed to talk about them because we don't want to get scooped. So there are people working on it.
Okay, cool. Thanks. Good luck with it.
Thank you.
Okay, a couple more questions in the chat, Michaela. Allie Payne wants to know what you're going to do after you get your PhD.
My plan is to go on the academic job market. So what that will look like for me is doing a couple of short-term postdoctoral research positions, either at universities or at NASA. And then ultimately, I would like to get a tenure track faculty job, which is what everyone who's getting a PhD says, really. But I'm really interested in teaching and working with students. And primarily, unfortunately, in the astrobiology field, there's really only funding from NASA. And so you either work for NASA or you work for a university that NASA gives money to. And so I'm interested in going the university route because I also want to teach and work with students, but primarily astrobiologists end up either at NASA or at universities.
Okay. And the next question from Al Kwan is, what experiences did you have while living on Bainbridge that most inspired you to go on to study astronomy?
Yeah, I mean, I would say definitely like being exposed to astronomy and looking through telescopes and all of that at like a young age. Definitely like started like my interest in astronomy. I also remember sort of around that same period of time, I would just go to the library and I would just go to the like astronomy section. I would just take a bunch of books and I would just check them out and take them home to read them. So I think there was a lot of just sort of being exposed to astronomy and being interested in it that while I was on Bainbridge, I think was really what interested me in astronomy, even though that wasn't like, I wasn't dead set on that. Like when I started college, I was sort of like trying to figure things out a little bit more there. But it's one of those things that sort of looking back on it now, I'm like, of course, this is where I ended up. Like, what else would I have done? So I will say that I think starting from a really early age definitely helped me stick with it and stay interested in astronomy.
So, along those lines, then, who were some of your influences? Like, were there authors or professors or mentors, or where did you find inspiration? What people inspired you?
Yeah, so I would say, like, particularly as an undergrad, I had the opportunity to work with Vicki Meadows, who actually, it turns out, is one of the leaders essentially in the field of astrobiology. It's funny, I actually just basically sent her an email one day out of the blue, and I was like, hey, like, I'm interested in like astrobiology, like, is there anything I can do to sort of like get involved? And she essentially, got me started on research, helped me publish a paper while I was an undergrad, got me connected to my advisor now, helped me get into graduate school. So I will say I owe her a significant amount for really rooting me in the field and kind of understanding what it would take to get to like a career there, as well as kind of developing the necessary skills for it.
And that name again was,
Victoria Meadows.
oh, Vicky, you said. Okay, Victoria
Mhm.
Meadows. Okay. And and you knew her at UW, did you
Yeah,
say?
yeah,
Yeah,
yeah.
okay.
That's
All
right.
right. I imagine she's published some books.
Yeah, yeah, a couple of them that she'll like cancel her meetings for like a couple weeks, and she'll be like, "Oh, sorry, I have to like work on the book." So she's got a couple books. Yeah.
Okay, great. I'll look for those. All right. There's another comment from Raven who says, "I think you'd make a great teacher!" Exclamation point. Love it.
Thanks, Raven.
And Dave wants to know which exoplanet do you think has the best chances of finding a true biosignature in the next few years? Which true biosignature do you think will be found first?
I think honestly, in the next few years, we won't have the tools or the ability to collect data to definitively answer those questions. I honestly think, with James Webb, we'll be able to say, okay, we can see that there's, maybe some methane and some carbon dioxide, maybe some oxygen on this planet. But depending on like the signal strength and the concentrations of those gases, you could maybe try to speculate about what's going on the planet. But we really need a lot of spectra in pretty decent resolution to sort of like answer those questions. So I know that's not answering the question at all, but I don't think it will unfortunately be possible in the coming, maybe in like 20 years.
So what your research is doing is um, preparing the models that will be used to compare to those data once that those data can be collected. And we're still many years off from actually collecting the data. And I'm seeing the parallel. I've been fascinated by LIGO, and that's what they do. That's how they find black holes, is they've done all this work to build models of what different black hole and neutron star configurations would look like. And that data is already is available to be compared to the data as the data comes in. So that's essentially what you're doing.
Yeah, yeah. I mean, people have started working on these projects, right around the time when exoplanets were starting, to be discovered back in the 90s and whatnot, and they'll probably, be retired at least, before we ever actually find any of these data. So it's one of those fields that you spend a lot of time and energy in, knowing that you may not ever actually see anything from it, but that it is laying really important groundwork to someday in the future, whether that's in 20 years, which is still within the span of my professional career, or like 100 years, which is not in the span of my professional career. But hopefully, the work that I do is setting the stage essentially for that to happen later.
Get your name on enough papers and they'll have to cite you even 100 years from now.
Hey, that's the plan, right? That's the whole thing about like academia, right?
So I think, let's see, I thought Joe had his hand up again, but now it went away. So Joe, did you have another question? Joe Hutchings. Oh,
Yeah, this is kind of far afield. This is beyond the lecture and beyond, but for the sake of conversation,
Sure.
um, any comments about moons? Especially since we found so many Jovian and super Jovian things that it's beyond the kind of examination that you've been talking about. But for the sake of conversation, any thoughts about moons?
Yeah, so I actually think exomoons are really interesting, and I actually tried to talk my advisor into like putting me on a project with them, but he was basically like, we've never found an exomoon. Like, there's not really like much to work on in that area, which is fair. And that's really the problem with exomoons, is that we have enough trouble finding exoplanets, and exomoons are even more of a smaller target than that. I do think exomoons are really interesting and exciting, especially because all of those Jupiter, Jovian-sized planets that we're finding, a number of them are in these areas that we consider to be potentially habitable. And so I look forward to like the point in which we can look at exomoons, because I really do think there's a lot of possibility, like we see in our own solar system, to have habitable environments, even where the traditional like liquid water habitable zone doesn't predict.
Okay, Dave had another comment in the chat. Uh, do you think technosignature observers will have an advantage until Web ELT or TMT is available?
Um, so I guess a little bit of my personal opinion here is I don't know that I think techno-signature observers have an advantage, because if you think about, and you guys are familiar with the Drake equation, right? The Drake equation attempts to predict the number of intelligent civilizations that we're currently like living at the same time as, via constraining a number of parameters. And one of those parameters is how many planets that evolve life produce an intelligent civilization. And I personally think that that number is probably pretty low. And so I think that there is a much stronger advantage to looking for biosignatures, because I think it's almost certain, and this is my opinion, I should be clear on that, but in my opinion, I think there probably is simple life out there, but the idea of an intelligent civilization, given how big and how old space and time are, respectively, it's very possible that we just have not or will not overlap with them. So I don't necessarily think that technosignature observers have an advantage, because they're looking for something that is inherently like much less likely to occur. And so I guess I just I'm not sold on techno-signatures, I guess, is the long and short of it.
Okay, and Allie has another comment, a question. What is a realistic distance scale for studying exoplanets? How far outside of our solar system are we currently able to search for life?
Yeah. So, these are most exoplanets that we're looking at are things that are, one, definitely within our own galaxy. And I think a lot of them are even like within our arm of the galaxy. So things that are, hundreds to thousands of light years away, but certainly not, millions or billions. Like if you look at galaxies, or, like supernova remnants or nebulae or stuff like that, those can be really far away. But with exoplanets, we are looking a lot closer to home, just 4 light years. But one thing I will also say on that is that, there are constraints with direct imaging, even, and even if we could put like a 30-meter telescope into space, we'll really only be able to directly image planets, I think, that are like 12. I really want to say 12 parsecs from us, and that's only like 15 planets. So even as technology continues to advance, barring any huge leap in our like ability to construct mirrors and like exoplanet observation technologies in that way, we are really going to be constrained in terms of direct imaging to just that like handful of planets.
And one more question from me. Early in your talk, I heard you mention citizen science opportunities as follow-up observations. I wasn't sure I understood exactly what um, that. I know what citizen science is, but I wondered what opportunities an organization like BPAA might be able to participate in to further this research? Is that even possible?
Yeah, so I know when you and I were talking before the show, I was talking about a postdoctoral researcher who I've worked with who uses his own telescope to do like some follow-ups. So I actually will get in contact with him about like what organization he's doing that with, and see if I can pass that information on to you all, because it really is these transit observations which you can make with not space-based giant telescopes. So I don't have that information, but I'll forward it on to you. I also see
Okay,
there's a
great.
question from Steve about Tabitha Star. I must say I'm not actually familiar with where that is, so I do not have any updates on that, unfortunately.
Okay, it was just
Tabit-
curiosity. It was Tabitha Star just is a transit star with some really weird non-reoccurring eclipses. So
Oh,
it's a very interesting star.
that is very interesting. I'll have to look into that, but it's not something I've like come across before.
Okay, and Dave has asked another question. Do you include phosphine in your model?
So, not at this time. So the model that I work on, it is kind of a large undertaking to add new elements such as like phosphorus into it. And we actually are currently working on looking into phosphine. However, so there's a paper by Clara Souza Silva from last year that discusses the potential for phosphine as a biosignature. And to detect phosphine on an exoplanet, you're looking at an entire planet covered in a layer of phosphine producing bacteria. And I should also mention that the connection between phosphine and life here on the Earth is not super well understood. So I'm not exactly like breaking down the door of phosphine, just because while it is a potential biosignature, it's again something that's going to be more like a second line biosignature, just because it does have these complications. And also, frankly, anything related to phosphine right now is just kind of radioactive. And so I'm not particularly interested in digging in too deeply. I see that Dave also wrote, how likely would it be that phosphine can be detected in even the closest exoplanets? And like, again, that comes back to the levels of atmospheric buildup that you need are essentially saturating your atmosphere with phosphine and when you have to have an entire planet covered in sewage, basically, to get those phosphine producing bacteria. So it is a biosignature and it definitely has its uses, but I would say we're not at the point, I think, where it's realistic to think about looking for phosphine, just because we would expect it at really trace amounts. And then to detect it with James Webb or something we have in the near future is what would require like an entire planetary layer, which I'm not convinced on either.
That's a lot of sewage.
Yeah, pretty nasty, personally.
Um, okay, I think I'm not seeing any more questions or raised hands, so I am seeing a lot of congratulations sprinkled through the chat. So we'll be sure and to send you a copy of the text file for the chat, so you'll have that as well as the recording. And someone says
Great.
they look forward to reading one of your books soon.
I'll have to finish my papers first.
Yeah.
But I just wanted to respond to Dave's question really quick, which was, do you think periodic changes in CO2 is a good biosignature? I think it's very interesting. I don't know how much I'm actually allowed to say about it, but we are working on a project in my advisors group that looks at periodic changes, and specifically thinking about like seasonality and how that might also relate to the idea of biosignatures. So I think there's definitely potential in more like temporally variable things.
Okay.
So I've got a question.
Go ahead, Nels.
Okay, how would you say this? This is along the lines of the techno signatures, I think.
Sure.
But let's say hypothetically, there's some people out there, such as we are, 10,000 light years out there. Would they be with our technology, would they actually be able to see us or detect our presence in the universe?
Well, I think the main issue there, right, is that distance equals time. And if they're, existing right now, they're looking at the Earth as it was 10,000 years in the past,
That's right.
which is not like the civilization that we have here today. So I think once you get into distances that are that large, you start running into sort of more problems like that. I think it would really depend on like, do they have like James Webb level technology? Do they have technology that's hundreds of years like in the future to us? It really depends on like what technologies they've developed, or even if that's something that they've decided is a priority, which then you get into like alien psychology, which is like really really getting a little out there. But I think there could be other civilizations out there that aren't looking for other life because it's not something that they find motivating, or it's not something, looking to the sky isn't something that's like important or like meaningful for them. So I think it's possible, but I think there's a lot of like ifs between here and there.
So radio has been in existence for about what, 120, 130 years, something like that. So if there was a planet 100 light years away
Yeah.
that was listening for radio waves, they could hear
Yeah.
our first transmissions.
Yeah, it's like I Love Lucy broadcasts or something that are like out there. I think they've like officially like left the solar system or something.
Right.
But yeah, so I mean, there is that possibility for things that are within those reaches, but it's also like at a certain point, once those signals have been going out for hundreds of years, we can pretty much eliminate the possibility of at least a civilization that's capable of communicating back to us existing in that range, because or something much more, there's a much more sinister idea, right? So there's this idea of the Fermi paradox, which is like, if the universe is full of life, where is it? And you get into a number of like really weird and kind of like morbid and wacky ideas. They're like, maybe we're in a zoo, like maybe where we haven't like reached the level where we're like allowed to like communicate with the galactic civilization, or like so I forget where I was going with that, honestly.
Technosignatures.
Yeah, but so yeah, so at a certain point, we'll be able to at least eliminate that those civilizations within 100 light years of us are either there are no civilizations there, or they're not capable of communicating back to us, or they're doing something weird. So those are the options that we have to choose from, and I'm not really sure. I think it's getting really out there to assume something like we're in a zoo for the reason why we haven't seen any life. I think you can just apply, Occam's razor and say we haven't been contacted by an intelligent civilization because there isn't one that is like currently within the range of contacting us, or we're not their priority, or something like that. But I think you can get your mind really twisted around in all kinds of ways to come up with like, oh, like the aliens are here, but they're not talking to us, but they're only appearing in the upper atmosphere. And it's like, I don't think that makes a lot of sense. I think you can just sort of apply some generous uses of Occam's razor to kind of conclude that it's probably not it.
Yeah, I think
Yes.
one of the other things I think about the technosignatures is that if you look at the radio transmissions, for example, the initial radio transmissions were pretty wide open, pretty simple modulations. Currently, all of our radio transmissions are phase shifted, multi-frequency. Basically, they look like white noise very quickly. And so that's kind of another, how does the technology evolve? And if you're looking for a technosignature, it may be hitting you in the face and you may never know it.
Yeah. I mean, there's the famous story, right, of the guys who discovered the cosmic microwave background, and they ignored it for a number of years because they legitimately thought it was the microwave that was like at the observatory that people were using for their lunches or whatever that was producing those signals. And so there was something else I was going to say. Microwaves. Oh yeah, and there's a very chilling like short story actually that like it's like it discusses like the first communication we receive back, right, from another intelligent civilization, and the communication says only be quiet, they'll hear you. Which is of course the idea that there's some other civilization that, should we be signaling into the void? Like, is someone gonna come and like eat us or whatever? Um, so, again, that's starting to get way more into like the sci-fi like lane of things, but there are legitimate areas of research and thinking about like what should we do to communicate with extraterrestrial life, and how do we do that in an ethical way that sets them up on equal footing as humans, and doesn't immediately start with them being treated as like less than or something, especially given like colonialism and some like not great stuff that's happened on this planet. That really sets a lot of frameworks for thinking about, and even in terms of planetary protection and expanding the places where humans have been, what is our responsibility to those places, particularly if we find that they are inhabited? And I honestly think that we're probably not ready to be like an interstellar system. I just don't think we quite have the maturity to, what if we do find a planet that has life? And I'm not confident that it wouldn't just immediately be exploited in some way or another. And that's just me being kind of cynical and off topic here. But, I think there's a lot of concerns.
We can't even keep our own room clean, let alone go into somebody else's house.
Exactly. It's like the whole idea that it's like, oh, well, if we, make the Earth uninhabitable, we'll just go to Mars. And it's like, that's a terrible idea. Like, if we can't keep this one like working, we're gonna go to another planet, make it so we can live there, and then inevitably like repeat the same cycle. Like, that's not fixing the problem. And so I don't necessarily think that like interstellar travel is like appropriate at this moment, which the good news is it's not really possible. But I think there are actually on the like philosophical and like ethical side of things a lot of questions that need to be addressed before we're really prepared for the possibility of even just expansion, but especially like an alien encounter.
Yeah, actually, Michaela, I appreciate your cynicism, because there were a couple times when I was going to add in, it's like, yeah, there's questions on whether there's intelligent life on this planet at times.
Yes, I mean that's a fair point there as well, and I think yeah, there is a slowly growing area of the astrobiological field that does think about ethics and answer these questions, and NASA has its planetary protection program, which is designed to prevent us from taking microbes to other planets. But what's sort of the reverse of that? If we're deliberately taking our life somewhere else, what responsibilities do we have to that planet? And I don't think I really worry, especially with the increased like of space travel and all of that, that's something that's going to become really overlooked in the race to to settle, to expand, like Nell says, Earth first, Mars second in the destruction list. So
Yeah. Yeah. Someone has nominated you for first president of our solar system.
he used to be my boss, so I'm not sure he counts.
Oh. um, okay. Well, I want to say that at the peak, I saw 40 participants on the call, Michaela, and that's some kind of a record for us for when we've been doing Zoom. So
Well, I'm really thankful for all you guys who did come to see my talk, and I'm glad you all seem to have enjoyed it for the most part. And again, feel free to get in contact with me later if you have any questions or anything.
Okay. Well, thanks. Thank you so much. And thanks everybody for sticking around. I see people waving their hands in the little Hollywood squares over there. So that's great. Okay. Well, we'll let you go.
All right.
And we look forward to seeing you again sometime soon. This
Yeah,
was great.
of course. Thanks again, everyone. Bye.
Bye, Michaela.